So you can enter the data directly in via the command line if you've got a nice small data set. However, that won't work with decent sized data sets that you might encounter in practical examples. You're there all day trying to enter the thing on the command line. The easiest way to do this is to extract the data from another drive, and it's easiest if you've actually saved the data to a USB stick and then the file path is shorter. So my suggestion of how to do this would be to save the data as a .text file, and the easiest way to do this, if you've got, for instance, a data set in Excel, is to open Notepad on a My computer, Windows computer. You need Windows accessories, Notepad, and then what you could do for these examples: copy this .text file from Canvas onto USB stick, and then it's the commands as follows. So the read.table command applied to the full file path. The drive E is my USB stick on my computer. It might be different for you. And then what we should do here is, we've got this one around. 2007 score goes to the first column of this thing. 2009 score goes to the second column of this thing. And then it just repeats what you've done before. Difference goes to the 2007 score minus the 2009 score, and then just apply the t-test to the variable difference. Now the solution in R is as follows. So the thing to watch for here is this t-value is the same as we calculated by hand. The value here is less than 0.05. The thing that would be useful here is the mean, which is positive. So that is important because this thing is less than 0.05. So R, in common with any other software, gives you a lot of redundant information, but the interpretation is deceptively simple. So what's going on is actually much more simple than might seem to be the case once you see what R produces. And it shouldn't matter whichever method you use, you should get the same numerical results and interpretation at the end. So the way I would interpret this, so because this p-value, this is 4.861 e to the minus 13, which is 4.861 times 10 to the minus 13, because that is less than 0.05, then this gives you evidence that the mean is not equal to 0, and then the mean of x is this thing here, 72.33, which is positive. So this gives you the second sentence here. The mean difference is positive and significantly different from 0, and this suggests that the consumer confidence is higher in 2007 than in 2009. So the thing to watch for here, this gives you a reasonable interpretation that the crash has indeed affected consumer confidence, and you get the same numerical answers as we got by hand. So if you've got access to eViews, how you would enter the data would be as follows. So file, new work file, and you will then be prompted for the work file structure type, and then what you would need to do would be select unstructured, undated, and then enter the number of observations in your sample. Okay, do is create a blank worksheet which you can then populate. Probably the best way to do this is to copy data in from Microsoft Excel, although you could enter the data yourself once you create the spreadsheet as directed on the next slide. Now if you haven't got access to eViews, don't worry. I would prefer that you prioritise doing the examples in R. It's not necessarily easy to get hold of eViews at the moment, given that we've not got access to the campus and there are licensing restrictions with eViews. It's possible you might be able to get a student demonstration version of eViews. I tried to get a demonstrator's version of eViews and wasn't able to do so. So it's not necessarily easy to get hold of eViews if we've got restricted access to the campus. So this might look a little bit fiddly in terms of how to enter data into eViews, but it is logically constructed, and this is actually more efficient than alternative ways of doing this. So the easy way to do this is to generate a vector or list of zeros, which you can then edit as the second stage. So when it says edit there, this means that you can either type the values in yourself, or probably more realistically copy the data in from a separate Excel file. Okay, and what you would do then is, if you had a sort of large data set in Excel, you'd follow these steps for each column of the Excel spreadsheet. So what you would do is click on the Generate tab and enter x equals 0. This will produce a vector list of zeros called x. Now you can call this whatever you like here. Usually better if this is sort of logically constructed, and the simpler the better. Double click on x to bring up the spreadsheet of x values, which will just be a load of zeros in this case. And then on the top ribbon, you will click on the edit plus minus button, and then you can edit these values as we said. So you can either type in the x values by hand if you've got a small sample, or Excel file. Excel file with multiple columns, you have to do this in turn for each column of the Excel sheet. Now, I've tried to save you as much as I possibly can some of this sort of data entry, so I've got this one sample t-test work file available for you on the Canvas module page. So file and then thing up into sort of spreadsheet mode, and then in order to perform a one sample t-test, this is menu driven and logically constructed. You would need to do view, descriptive statistics, and test simple hypothesis tests. Now I ought to say here that you have to have this in spreadsheet mode in order for this thing to work. Okay, so if you try to do this and it's not working, you need it in spreadsheet mode by. Now once you've done this, this gives you sort of the same results as we've got previously, but expressed slightly differently. So there are artificial differences here, both in terms of when you're doing the hand calculation and when you're doing the computation in eViews, and when you're doing the computation in R and the computation in eViews. Okay, but the important thing is you should be getting the same numerical value and the same interpretation in each case. And here what you've got is that the p-value is less than 0.05, so an indication that the mean isn't. So in terms of the one sample variance ratio test then, so there's two central questions in statistics for a generic data set as we've seen. These are the location and the spread, and the easiest way to sort of transfer these into directly usable statistical qualities is looking at the mean to measure the location and the variance to measure the dispersion or spread. So the first question is, what is my best guess of the value? The second question asks, how far away from the true value am I likely to be? So to answer this first question then, use the one sample t-test. Second question, use something called the one sample variance ratio test, which is a chi-squared test. So there are two different versions of this chi-squared test which we'll go through in this lecture. Now, to answer the second question, you're using a different test, this one sample variance ratio test. This uses a different chi-squared distribution and a different set of tables if you're doing this by hand. Now, it's not as natural to use as the one sample t-test, but might still be useful for statistical work on MSc dissertations. And with regard to some of the dissertations I've supervised in the past, even these simple statistical methods can be useful for on accounting and finance. So to illustrate this one sample variance ratio test, we've got this illustrative example. So we've got the following data trying to match consumer expectations and consumer spending in 2011. So the top table gives the consumer expectations for each month of the year. The consumer spending is given on the second row of the table for each month of the year, and the difference in the bottom row of the table is the consumer expectations minus the spending. I hope that if the consumers are sophisticated, that there would be very little gap between the expectations and the spending. Slightly contrived example here, but you're asked to test the null hypothesis that the standard deviation is equal to 1. Now, again, this is a sort of slightly odd way of phrasing it, but to try and sort of put this in more concrete terms, if the standard deviation was equal to 1, then equal to 0.95, I should say, the consumer spending index would be within 2 standard deviations of the consumer expectations index, so within 2 of the consumer expectations index. Now, as I said before, the more sophisticated the consumers are, you'd expect the smaller gap between the expectations and the spending. Good outline then of the variance ratio test if you're calculating this by hand. So the first two things you have to do are to calculate the mean and then to calculate the variance, and then you would need to use that to calculate the chi-square statistic. So squared comes from the variance that you've calculated in the second step. The sigma squared would come from the value of the variance from the null hypothesis, and you would then compare against the chi-square distribution with n minus 1 degrees of freedom. So n is the number of observations in the sample, and loosely speaking the idea is because you're estimating one parameter, here the sample mean, in order to calculate the variance, you lose 1 degree of freedom. The basic idea comes up again when we look at regression models. So in the situation with regression, you're estimating pre-parameters. So in this case, you use freedom, and you're left with n minus b degrees of freedom for the residual. So it's good practice in terms of the mechanics of the mean and the variance calculations. See similar things with the more advanced regression techniques used. Following on both from the earlier part of this lecture and from last week's lecture, when we look at the one sample variance ratio test, there's some important calculations that you have to do. So the first thing you have to do is to calculate the mean. Before, all that happens when you calculate the mean is you take all the observations in the sample, you add them all up, and then you divide by the number in the sample. Calculate the variance. Top equation in the second bunch of equations gives you the practical calculation formula. Note the n minus 1 for the bottom line of the fraction, and this is the practical calculation formula to give you some simplification based on some of the formulas often used in corporate finance books. Some of the xi squared is just all that happens there to calculate that. So you just square all the observations in the sample. You should get the value for the standard deviation of 76. I should say value of 76.8182. Detailed calculation there on the slide, and I would say just make sure that you take your time plugging the numbers into these formula. Don't rush it because you can then make a bad mistake. If you're doing the hand calculation by hand, I would suggest sort of splitting this up into sort of 3 separate steps. So the first step is to do the calculation. So using the results from the previous slide, the chi-square 845. So from the tables, the chi-squared value for 11 degrees of freedom is 2.01, which is 5. So 845, the chi-square statistic is bigger than the value in tables, therefore p is less than 5. So we reject the null hypothesis that sigma squared equals to 1. Now the next bit, the interpretation, which would be what you would need for this course. It's not just a purely mechanical process. So you would reject the null hypothesis, sigma squared equals to 1. The true standard deviation appears to be much larger. A better estimate for sigma would be the sample standard deviation, which would be the sample variance, which would be 8.765. So if you have this, value for the standard deviation. This suggests that with probability 0.95, consumer spending index will be within 17.5% of the consumer expectation index. So potentially quite a big mismatch between consumer expectations and consumer spending.